In this video, I want to talk a little bit about how we analyze performance of systems that use the paging system. So basically, right, we're kind of having this idea that somehow my system's going to be slower, right? Instead of assuming that everything's going to be in main memory, I'm now going to say that some of it is in main memory while some of it is on a hard drive somewhere, right? So I want to kind of figure out how much does that hurt me. So let's go through a little bit of a setup here, and then we'll do some analysis. So first thing is we'll define P. P is basically going to be the chance, right, that a request causes a page fault. Okay, so P, of course, right, is going to be between 0 and 1. That's my bounds, right? It's a probability. So here's a question for you guys. Think about it for a second. What is the meaning of P equals 0, and how do we get it? P equals 0 basically means that no page faults occur, right? There's a 0 probability of any faults occurring. And that's typically only going to be the case if we have effectively an infinite amount of memory, right? We're never going to actually need to move anything out to a secondary store. Everything can just be in main memory all at the same time, right? So this is kind of the case we had initially, right, when we first talked about main memory. Everything can get stored, no problem. Second question for you guys: what is the meaning of P equal 1, right? And how would we get it? So think about that for 1 second. P equal 1 basically means there's a page fault every single time, right? So there's a 100% chance of a page fault. Where you're going to get that is basically in a system where you just have memory for one page, right? So if you can only load one page or one frame at a time, well, then every time you access something, you're going to kind of be constrained, right? You're going to have to keep on flipping out things, right? And it's going to be kind of very, very, very slow. And actually, as a side note here, we can't really have a system that only has one frame in it because we have operations, right? Opcodes. That require accessing more than one place in memory, right? So if your opcodes can do something like add two numbers and store them somewhere else, right? Then that means basically what we need to have is 3 different frames available. We can't do it all in one frame, right? Because I can't hold all of the memory that I need to run an operation kind of at the same time, right? I need to have at least enough memory to run those operations. So I'd probably need something like 3 slots at minimum. Okay, so let's define a couple of constants here, and we'll use these in expressions on the next page. First I think we have here is mem_access. So mem_access is basically going to be a constant that represents how much time it takes me to access main system memory. The second thing here, right, is basically going to be the time to recover from a page fault. So that means going to the hard drive, detecting a page fault, going to the hard drive, picking a victim frame, moving it into main memory, right? So this is basically my cost. So this is basically my cost here is low for accessing main memory versus my cost over here is high for using having to go to the hard drive and pull something from it. So these are going to be my two kind of symbolic things I'll use to represent the amount of time those things take. So let's try writing a simple expression that uses these. So given that we have basically those two things as known values, we can define what is called effective access time, or just call it EAT. So EAT looks like this, right? We have basically 1 minus P times memory access plus P times page fault. So what that's doing, right, is it's taking basically an average, right, between the pages that don't have page faults and the pages that do have page faults. And then we're multiplying that basically in terms of what is the chance it will occur. So overall what we get is that effective or average or expected, you could use any of those words, access time, right, based on how much, given that this probability, there's this probability of it getting data from here and then it costs this much, right, how much will we get? How much will it cost us? So that's our little formula here. And we'll try one example here. So let's say, for example, that our memory access time is 200 nanoseconds, our page fault time is 8 milliseconds. Well, then we want to know basically, in that sort of a system, right? And actually, I should have the last thing here as well. So then we're also saying that there's only one page fault in 1,000, which sounds pretty good, right? 1 in 1,000 is pretty good. What would be the effective access time? We can try to compute that. And so what we do, right, is basically plug in all those things into our formula. So I get this kind of long expression over here. I can evaluate that, and notice that I get basically 8,200 nanoseconds, right? I mean, it's off by a little bit, but that's kind of a huge number, right? And so I can compare, my nanoseconds versus this, right? So my RAM access time, right, is something like 40 times faster than my average or my expected time here. And that's kind of an issue, right? Because this thing over here, right, even though page faults are very infrequent, right, we're saying that they only occur 1 in 1,000 times. The problem is that my page faults take forever, right? They take 8 milliseconds. And so when I go and do the math, right, I get this huge kind of average thing because every time I have a page fault, it just slows down everything else, by such a huge margin. So this is kind of a, this is what we get, right, if we evaluate the formula, but it's not really the answer we want, right? This is a little bit too slow for us. So what we can do though, right, is basically use this formula to find something that's maybe a little bit nicer, right? So right now we're kind of fixing the number of page faults that are going to occur. But what we could actually do is we could actually solve for the number of page faults that could occur, and then we still get a decent amount of time. And so that's actually what we'll do next. So what we're going to say is the following. Let's see if we can basically figure out how many page faults would be necessary if I wanted to basically have these two things be off by only 10%, right? That sounds a lot more reasonable, right? I mean, before we said they're basically 40 times different, right? Here we're saying, can they be off by 10%? So let's see if we can do that. What we'll do here, right, is basically use the same formula, right? So we'll use the formula from up top, the EAT formula here. We'll use that. We'll substitute in. We'll put in basically our effective access time as being 220, right? And then our memory access time is 200, right? So I'm going to basically put those values in there. They're different by 10%, right? That's kind of where our bound is coming, because what we want to do, right, is basically solve for P, right? We want to solve for the number of page faults that gives us this performance. And so we know, right, that it's going to take 200 milliseconds to access our main memory. We want to say that, in terms of, this EAT, right, we want to make that be, about 220. We basically put those in, right, and basically try to solve for P. And so that's what we have here, right? We put them in, right? Try to solve for P. And in this case, right, we get, so we do algebra here, right, algebra here. In the end, right, what we solve for is P equals this value here, while at the very end it ends up being basically 1 in 400,000, right? So if I want to have my performance only be off by 10%, I need to have only 1 in 10,000 accesses cause a page fault. So this, right, is a little bit of an intimidating number, but if we want that performance, that's what we're going to have to aim for. And so we're definitely going to need to talk about all different sorts of algorithms that basically can do that selection of, what pages I keep in memory, because that's really going to give me this number over here, right? I want to have some smart way to keep things in memory. Otherwise, I'm going to just trigger too many page faults. I'm going to get in trouble. I'm going to get really bad performance. So yeah, that's going to be kind of our next stop, right, to talk about algorithms that we can use to basically pick, what should be running or what should be kept in memory, right, and what should be kicked out of memory.